There, starting the recording officially. So, happy not garbage day. I am so messed up today. Not only is it like, feels like a Monday, but it's not garbage day. So tomorrow I'm going to be like, is it garbage day? Am I teaching? Like, what is going on? So, yay, Labor Day weekend. Anybody do anything fun? No? You're like, does napping count? No. You did? Excellent. Family trip to Chicago. That's a good use of a 3-day weekend. We took our son bowling yesterday. I don't know if you've been down to Colonial Lanes. I'm going to put a shout out to them. It is like a 1985 bowling alley. Like you can still like feel the cigarette smoke. Like it's old. And I mean that in like as a positive way. Like it's the bowling alleys of my youth. It's very like lowbrow, like no fancy screens, no fancy anything. And shoe rental is $2 and it costs $5 to bowl a game. And they have student discounts on one of the days. So highly recommend if you're looking for a place to hang out. Happy hour from 3 to 5. Yeah, you can get out of class and then, go bowl and play pool and have a good time. With good hot dogs, I haven't tried the hot dogs. They do have food there, though. I can tell you that much. Maybe a GMAS outing. Just saying, little group thing. So we're all back. We're heading into week 2. So things you can be working on, homework 0, you can give a try if you haven't done that already. And if you can't get in for whatever reason, like I screwed up the database, which is entirely possible, please let me know and I'm happy to fix it. I will let you know when the next thing is available, which will be, I think, your first formative assessment, not for 2 weeks or so. So we're kind of easing into the semester, as it were. We have the start of lecture 3. So if you haven't grabbed that off the webpage, please do so, and we can dive in. The idea of this is to sort of transition from a regression, one outcome per person type of framework into a multiple outcome per person type of framework. And I want to connect this explicitly to analysis of variance because that's one thing that people often get confused by is how is multi-level modeling different than that and how is it the same? And there are definitely points of overlap and points where multi-level modeling adds choices to the mix. So away we go. So 2 sides of a model. We introduced this vocabulary last time. You're going to hear me say this quite a bit this semester. Model for the means versus model for the variance. Model for the means concerns the predictors, what they are, what kind of effects they have, how they work together to create some kind of predicted outcome. And the coefficients right here, beta 0 as an intercept, beta 1 and beta 2 as the slopes, you will hear me call these fixed effects because they are constants. In this equation, the same beta 1 would hold for everyone in building their predicted outcome, the same beta 2, and so forth. The model for the variance on the other side is just E. It kind of looks strange to think of this as a model, but yeah, like putting an E here is the representation of an idea. It's the idea that we have one source of unexplained error, so E is considered a random variable in the sense that it has a distribution. We say that it's normally distributed, in fact, and that means that it's supposed to have constant variance and it's supposed to be independent across people. So this model for the variance is going to be inadequate anytime we have more than one observation, because at a minimum, you would expect the occasions from the same person to be related to each other. So this is designed for, I call this a between-person model sometimes, or you might hear between group. This type of model is designed for data in which there's only one dimension of sampling, not 2. Just to remind you that you've seen some of this stuff before, means, variances, covariances, and correlations. You're going to see a whole lot of this semester. We all remember what a mean is. Variance is squared offnesses, so distance from the mean squared, add them up, divide by n if we're talking population version. Covariance is one that you might not have seen in a while. I just want to remind you what it is. It is unstandardized correlation. So it's how far off on one variable times how far off on another. And the problem with covariance, is that you don't have an intuitive way to think about what size is because it's in whatever units you have. So if we were talking about the relationship between, say, inches of height and pounds of weight, or kilograms and meters or centimeters or something like that, like you would have covariance in foot-pounds or meter grams or something, and no one knows what that is. You can say that a positive covariance, that means if somebody is above the mean on one variable, they're above the mean on the other, and opposite if it's negative, but there's not an easy way to understand that. And that's where our friend correlation comes in. We standardize the covariance by taking off the units. So then correlations range from -1 to 1. So in what the unit we're in right now and heading into unit 4, you will see these things quite a bit. You will either see variances and covariances, or you will see variances and correlations. But you can get from one to the other. You only need to know mean, variance, and then one of these two to get back and forth. And software will differ in what they give to you as part of your model and how it's parameterized, whether it's expressed in terms of correlations versus covariances. Okay, so starting at the very, very beginning, the simplest possible model you could ever have for data is right here. I call this the empty model. Empty means model in particular, because the model for the means is what we're focusing on. It has no predictors in it. That's what empty means. So if I don't know anything about a person, what is my best guess for their outcome? What would a reasonable guess be if I don't know anything about a person? The mean. Yeah, people call that expected value, right? That's what we would expect, sort of naively. So if I were to develop a prediction for this person who's clear down here, the mean in this example is 90, as shown by the red line here. Now that happens to be not a great guess for this particular individual. They are off by 58, so their score is 58 lower than the mean, yielding a result of 32. So the model for the means is literally just this mean. That's where the term comes from originally. And then the variability of the e's would be computed using this equation here, how far off you are from what is predicted. So y hat is the notation I'm introducing. That's just 90 squared, and then divide by n minus 1 if we take into account the fact that we had to know what the mean is in order to make this work. So conceptually, this is our starting point. What we get back is the mean and the variance of our outcome. Then we refine it further, adding stuff to it. But this is not regression class. That's at 2 o'clock. I know that. I swear. I know where I'm going with this. What if you didn't have just one outcome per person? What if you had 5? That's what you're here for. So this idea of 1y per person, y sub I, is going to become y sub ti. T stands for time and I stands for individual. Let's say we have a blue person, a yellow person, and a purple person. So same idea. If I don't know anything about a person, my best guess for their outcome is the intercept, the mean. And more specifically, a fixed intercept is the part that everybody's going to share. But I do know something about a person. I don't know anything about their predictor values, but I do know from which person each of these observations came. So a better naive starting point would pay attention to that grouping and think about, well, not the same mean for everybody. What if I start by giving each person their own mean instead? That's a better guess. That idea of giving someone their own mean is going to become what we call the random intercept. Vocabulary term, fixed means everybody gets the same, it's a constant. Random means everybody gets their own, it's a variable. So what we are doing straight off the bat before we do any kind of prediction is splitting, partitioning the variability of our outcome into 2 different kinds, or reasons, or sources. Or you will hear me call these piles of variance. That's where the book's website came from, pilesofvariance.com. It was a birthday present from my husband many years ago, because that's what nerds do. They give each other domain names as presents. He got me lisahoffman.com for that same birthday. So, piles of variance. We have between person and we have within person. So between person is the idea of why is it that this blue person is so far above average, this yellow person is near the average, and the purple person is below. Something consistent and systematic about the person, because it's a mean difference that is constant over time. That's inter-individual differences. That's going to become level 2. But then relative to one's own mean, you don't have the same score at each occasion. Sometimes you're higher, sometimes you're lower. That's within person variability. You relative to your own usual amount. Intra-individual differences, and that's going to be level 1. So we're not explaining anything. We are simply partitioning. This is all still error conceptually because we don't know why some people are higher than others. Just we know that they are. We don't know why some occasions are higher than others. We just know that they are. Two kinds of error. So let's say, graphically then, I have some example fluctuation style data where there's no change on average as indicated by the heavy black line, but we have people just sort of bopping around their own levels. And I've got 5 hypothetical people here, 6 actually. So if I think about a between person model where all of the variability in y is still in one e, like each e would be defined as the distance between where the person actually is at that occasion, so breaking down the purple person's data here, and the sample mean for that occasion. So if I give one fixed intercept, I'm assuming no change over time. And then all of this variability represented by e at time 1, all of this, so e at time 2, e at time 3, and so forth. Well, right away, I know that a standard regression model is not going to work for this. E's are supposed to be uncorrelated, right? And the fact that these are all below the mean, that induces a correlation. So we can fix it. What we're going to do to fix it is split it up. So if I give the purple person their own mean, then the distance from the sample mean given by the black line and their own mean given by this dashed line is going to be covered by a new letter. Meet your new friend U. U is for each of you. Also, U is a letter I can draw and type reliably. That is the number one factor in how I choose my notation. What am I capable of drawing with a marker or with a mouse if I need to? So U0 in particular, that is a random intercept. It has an I subscript because each person gets their own version of it. One U0 per person conceptually in the equation. From there, E is what's left. So at time 1, this person was lower than predicted by their own mean, so that E would be negative. At time 2, they're above it, so that E would be positive, and so forth. So now, to the best of my PowerPoint drawing ability, the E's look like they would be uncorrelated. Some are high, some are low. There could still be residual correlation, but you wouldn't see that in the plot. The idea is that all of the reasons why the E's were related are supposed to have been captured by this U0 random intercept. And once we control for that or factor that out, E's are unrelated just like they are in standard regression. Hit me.
So is UOI the mean for each individual, or is it the difference between each individual mean and the group?
I'm so glad you asked. It's the difference. Yep. So you have to put them together. The fixed intercept, the mean on average, plus the random intercept gets you to the person's full mean. U's or deviations. This purple person would have a negative U because they're below everyone else. The other colors on the sheet, I think it's rainbow order. Of course it is. I made the slide. The red people, the orange people, they would have positive U's. And then it would be about the middle for the green and the, what is this, cyan? Okay, we had a debate at my house as to what color cyan actually was the other day. And we weren't sure if it was the yellow or blue. It's the blue. Okay, that's right. Okay, I'll make sure I'll tell them. Apparently there's an issue in Among Us that the colors don't actually match. I don't know if any of you follow this video game. There was something like they were talking to each other and they're like, the imposter's in cyan. And my brother's like, what's cyan? Or my son is like, what's cyan? So that they don't match, apparently. So, question from the Zoomers, why is it U0? Because it's beta 0. So it's the intercept. And yes, does that open up like a U1 or a U2? Or yeah, that's where we're going. By the end of the semester, we'll be at like U4. Yep. The idea is that like each term in the model that's measured at across time can potentially have a U that gives each person their own version of that slope or that intercept. That's where we're headed. So putting it on the other slide then. U0 is how far off from the grand mean your mean is. So the blue person has one, the purple person has one, the yellow person's is right there, very tiny. But just like in regression, how we don't really care what E is per person, we track its variance. We're going to do the same thing. So U0 is the idea that there is a variance across people in these random intercepts, in the deviation from the grand mean that gives each person their own mean. In terminology that is consistent with other multi-level textbooks, it's going to be this thing is tau squared, that means variance, and my convention is always to use the subscript to say what it is the variance of, because we're going to have a lot of them. So this is the variance of U sub 0 specifically. So the variability across individuals, that's what we're adding to the model, not each individual U0. Otherwise, that would be kind of a nightmare, because if you have a really large sample, that would be a lot of extra parameters as opposed to just one variance. So U0 is the idea that each person needs their own intercept. The deviations of the U0s across people from the fixed intercept, that's my level 2 random intercept variance. Between person inter-individual differences, macro is another word you can add to that. Am I forgetting any? Synonym party? Between, level 2, macro, inter, U0, random. Put all those words in a stack in your head together. That leaves then, as the alternative, level 1. So the E's that get you from where the intercept left off to where your actual occasion's outcome is, that's E. And E is per occasion per person, and yet our naive starting point is one variance that's supposed to hold for all times and all people. Now that's a testable hypothesis, but that's our starting point. So that's within person, level 1 variance, and you will hear me use the word residual very specifically for that. In this class, I'm going to try really hard not to confuse you. It's random if it's level 2 or above, it's residual if it's level 1. When we get to the part where we have predictors, and you're used to thinking about residual variance, then we would have something like the residual of the residual and the residual of the random, and that makes my head hurt. So instead of using residual in that, it's going to be leftover. We good with that? Leftover level 1 variance after predictors. Leftover level 2 variance after predictors. Residual is reserved for level 1, and level 2 is random. So in equation form then, we're talking about empty means single level model looking like this. So beta 0's fixed intercept would just be the overall sample mean across the entire column of data, not paying attention to particular people and which occasions, just one straight up mean. E would be the distance between that mean and that person's single outcome. Our 2-level model separates out E into what is used to be just all E, but now it's leftover E and U. So we're splitting. Note the symbols. So Y gets a TI because it's per occasion per person. E gets a TI for the same reason. U, 0, only gets an I because it's not per time, it's only per person. So subscripts are everything in these models. And then beta 0 doesn't have an I or a T because it's for everyone. That's my fixed intercept. It changes interpretation in this context. It is no longer the straight mean of the sample, it is the mean of the person means. It's weighted. So if somebody has 10 occasions, they would contribute more to the sample mean than someone who has 5, but that's not going to happen here. This is the mean of the sample means. So it can wiggle a little bit after you add a random intercept for that reason. Ideally, we would be able to see the sum of the U0 variance and the E variance equal to the total of the original E variance, but that doesn't happen. It'll be close, but it won't be exact, especially in unbalanced data where each person contributes a different number of occasions. Okay, how are we doing so far? Can we do a thumb check? Okay, partially up and questions. Let's see. Okay, Zoomers are halfway up. Okay, go for it.
If we go back one slide,
Certainly.
I have one question about, so the level 2 random intercept explains the inter-individual differences from the grand mean. The level 1 residual variance explains the intra-individual differences from their own mean.
Correct.
Somehow in my head, I want those to be flipped, so I want the level 2 variance to come from differences from their own mean, and the level 1 to come from differences from the grand mean. Can you help me see where those connect?
Yes, so question was, level 2 intercept, I wouldn't say it explains, I would say it captures. Like that's what it means. It captures all the reasons why people need a different mean from each other. And that's considered level 2 because occasions are treated as nested within people. Technically speaking, and I think there's a slide about this, they're crossed. I usually lie at the beginning of this class, but I decided not to this time. Technically speaking, they're crossed. Each individual outcome is nested in people and it's nested in occasions, because if you think of it, it's like people are a row and time is a column or vice versa. It could go either way. But what's going to happen is that once we put in fixed effects that address differences in the means across time, that time dimension falls away and it's just strictly nested. So you can think of level 1 as like a time by person interaction. More technically, that's accurate, but we usually sort of take a shorthand and say time within person. In clustered data, I think your intuition would work. So in clustered data in which people are nested in, say, classrooms and schools, like the people are level 1, the school is level 2, or classroom is level 2, school is level 3. It's because we're adding information about the person that's like below them is level 1 in this context.
Could we say that these descriptions on this slide only apply to a 2-level model? If we have a 1-level model, then sigma is going to refer to differences from the grand.
Yes.
I want sigma to always be about everybody. But
Yes. Yeah, so in a 1-level model, the sigma E term here, the variability of the E's would be across people.
Okay.
Yeah, you're right. It switches. And for that reason, there are some authors who they save E for the people and then they add some other term. Those people usually use pi as their symbol in their model, and that drives me nuts because pi is 3.14, not a variable. So like my brain can't handle that. But you will occasionally see that for that reason. All right, Vladimir, were you waving to me?
Yes, I have
Okay.
one question because last class you said that random effects were latent variables.
Yes.
Can you elaborate on that, please?
Yes, I can. Right here. So this combination of beta 0 plus u0, that is a latent variable, is another way to think about this. Each person getting their own not say starting point, mean level at this point. Is a latent variable, where the mean of the latent variable is the fixed intercept. The variance of that latent variable is the random intercept variance around the fixed intercept.
Great, thank you.
Yeah, I'm not to the placeholder notation yet, but that is where we're headed. Yep. All right, who else had their hand up? I thought I saw one. Zoomers, are we good? Good? Okay. All right then. So then the first logical question you might want to know is, well, if I have these two different piles, how much do I have of each? Turns out there's a statistic for that. It's called intra-class correlation. You have probably heard this term in a number of different contexts. It is almost always some kind of ratio of variances. This one is known as ICC1 in the HLM literature specifically, and if you have that program, that's what it would say on the printout. This is your between person variability due to the random intercept, which is tau 0 here, or tau squared sub u0, divided by the between plus the within is the total, or intercept plus residual, or level 2 plus level 1. So I've written this like a bunch of different ways because they all mean the same thing. It's level 2 over total. And in a correlation form, just to remind you here, we would have the covariance between any two occasions divided by the standard deviation at each of those occasions. And according to this model, the covariance between any two is only due to the random intercept. So this is a statement, a prediction, if you will. What this is saying is that the only reason why time 1 was correlated with time 2 was correlated with time 3 is because some people have different means, and that's it. Once you allow for constant mean differences between people, what's left over is supposed to be uncorrelated. That's what this model is saying. So you will see the predicted, this is a new term, R matrix, variance covariance matrix across time, where what these rows and columns mean are occasions. So if I had 3 occasions, what I'm saying is the variance at time 1 is part E and part U. The variance at time 2 is part E and part U, and so on. Note that this is the same symbol on the diagonal. That is a prediction that the variability is the same no matter what occasion you're at. Likewise, the same symbol of random intercept variance on the off diagonal is a prediction that no matter which pair of occasions you have, they are equally covaried. And then if I change that into a correlation matrix, ICC is what's on the off diagonal. So you can think of this as how much of your total variability is due to person mean differences. Person mean differences, meaning cross-sectional variability, right? Mean differences would have been there to start with. You just wouldn't have a mean. You'd have 1 point per person. Once you get at least 2 points per person, then you can give each person their own mean. But this is how much of the total variance is because some people are higher and some people are lower. That information you would have had already. So that's one way to interpret it. The other is to think of it as a correlation. It is the expected correlation of occasions from the same person. Disregarding which occasion is which, assuming that those are all exchangeable. ICC can also be thought of as an effect size. Do you remember the term dependency? That was one of our vocabulary words from last week. Give me a one-word definition for what dependency means. Starts with a C. Correlation, yeah. So ICC is an effect size for the amount of person dependency that is constant over time. What proportion of variance is due to some people being higher and some people being lower? That's your interclass correlation. And yeah, you want to go there, yeah. So this thing ranges from 0 to 1, given the way that it's computed. A ratio of 1 would be what? All, which one? Between or within? Between. All people or all occasions? People. Level 1 or level 2? 2. Macro, micro. Macro. And one more. Inter or intra? Inter. Yeah, we're going to keep doing this every class. It's just, we're going to keep it, like, get flashcards and just, like, commit it to memory. Because the sooner you commit it to memory, the faster you'll be able to read the rest of the stuff. It's very hard at first. So if my interclass correlation is 1, that means all of my variability is in the random intercept. All of my variability is person mean differences. I don't have longitudinal data. That's what that means. My poor student that I told you about last time, that happened to them. They did not have longitudinal data, even though they asked the same question 5 times. So if we flip it then, what's an ICC of 0? That can happen. All what? Not a trick, I swear. Did you say it? Within, yeah. So if an ICC is 0, that means there's no between person mean differences. All of the information is time specific. That doesn't happen often, but it can happen. So in models where we have predictors related to time, the intercept is going to become conditional on time 0. So let's say that you're studying language development in infants and toddlers, and you start measuring them at 12 months. Well, a 12-month-old might know 1 word, maybe 2. They know it, they do a whole lot of babbling. And so if you think about mean differences, say, in vocabulary knowledge amongst 12-month-olds, there's not going to be any. Like, they're all pretty much at the same spot. But as they develop, they spread out. And so then you would have mean differences that emerge later on that might not be present at that particular time 0. So it can happen that your ICC is 0, but it doesn't mean game over. If your ICC is 1, that means game over. That means you basically just have a cross-sectional analysis, and you may as well just use either the mean across time or 1 point. But anything else, anywhere in the middle, play ball. All right, so what about adding predictors? Well, I can add in predictors that are time invariant level 2 things or time varying level 1 things. In a single level model, it would look like this. In a 2-level model with U in it, it might look the same, but I can have any predictors at any level that I want. And so then the interpretation of these residuals for E, random intercept for U0, changes. U0 then becomes all the reasons why people still need their own means after controlling for your person predictors. They're not going to be perfect, so U0 then becomes left over. The remaining deviation after you get to where they should be based on their predictors and what their actual mean would be. E as the same idea, it becomes left over. So after you add time varying predictors, E is all the remaining reasons why you are not where you're supposed to be at that occasion, based on person stuff and time varying stuff. So each of these things can decrease. Do you remember effect size in linear regression? R square? Guess how many we're going to have? In this model, 2. 1 per blue thing. When we get up to U4, that would be, if I count the 0, 5 level 2 variances and 1 level 1 variance, each predicted by different fixed effects, each partially explained to some extent. Yep. All right, I've got an example because I want to show you what happens in terms of our inferences about the test of our fixed effects when you fit a model that allows for correlation over time versus when you don't. These are fake data because fake data are always exceedingly well behaved. Canned data is the expression I've used before. This is straight out of chapter 3 of my book. So let's say that I have a 2-group design. I measure them both at pre-test and at post-test, and I'm hoping that people who are in the treatment group improve more than people who are in the control group. Fairly straightforward, typical design. What the values are in the table are the cell means, so for the unique combination of group and occasion, and then I believe these are standard errors, I think, behind them, not standard deviations. Yep, standard errors. The numbers in the boxes are the differences between adjacent cells. So for instance, 50.76 is higher by 1.68 than 49.08. 58.62 is higher by 3.72 than 54.9. The ones that are in red are the ones that we're going to see on our output. So going from left to right, 49.08 is lower by 5.82 than 54. Likewise here, the difference between these two cells, 50 and 58, is the 7.86. And the 2 in the middle is the interaction term for the difference of the difference, as it was originally explained to me in ANOVA language. The way that you can understand that from looking at these values is that 2.04 is the difference between the boxes. So 5.8 is lower than 7.86 by 2.04, going from top to bottom. 2 is the difference between these two boxes. It also holds from left to right. So the difference between 1.68 and 3.72 is 2.04. Every two-way interaction can be explained 2 different ways. How time has a different effect based on what group you're in, how the differences due to group matter more at one occasion than another. You can spin it either way. So part of what I wanted to do with this is not just show you the results in terms of the hypothesis test, but also to give us a little bit of practice with main effects and interaction terms, because those are going to show up this semester quite a bit. Not for a few weeks yet, but quite a bit. Okay, you ready for an example? Changing gears? All right, then I've got example 3A pulled up here. This is a separate handout that you have a PDF version of. All of the original source files that built this handout are inside the zip folder on the website right underneath it. So you can follow along and run things, or you can follow along with me in the handout. I've got syntax and output heavily annotated in here for Stata and R, not for SAS. That's on the online materials only. Okay, so first stop is to restructure our data into the kind of format it needs to be for multi-level modeling. This step was skipped if you were in the clustered class, because in that context, you have one observation per person and people are nested in groups. Your data would already be one row per person as the level 1 unit. I'm starting from a data set that has this structure on the left. This is called wide format. I sometimes call it multivariate. It's one row per person. So this is the first 5 people, all from group 1 in the data set. And I have outcome 1 and outcome 2 for their pre-test and their post-test respectively. One row per person. So this is like one row per level 2, with the columns telling you about level 1. That is the standard that you would use to fit this analysis using structural equation modeling software or traditional repeated measures analysis of variance. What we need is the one on the right. This is called long format or stacked. You will hear me use those interchangeably. Now note, because we used to have 2 occasions, we now have 2 rows per person. We have one column that holds the outcomes for both, just called outcome. And we have a new indicator variable for occasion that says which one it was. So I have occasion 1 and 2 as a column, and then I just have all the outcomes in one column now. So fundamentally, this software is univariate. You need all your occasions in one column and predict that one column as Y in the analysis. So you can think of this as like, this is YTI in this column, per time, per individual. Now the good news, every software package on the planet has a routine to do this for you within a few lines of code. You do not need to spend your summer break doing this manually in Excel, ever. So here is an example of what that would look like. First in Stata, then in R. So I'm setting my working directory. I'm importing this data set in Excel format. I'm using case preserve so that whatever case conventions I had were the same, so it doesn't convert it to lowercase if you have this option. The command that allows me to transform my data is called reshape. So there's reshape wide or reshape long. So I'm going from wide to long. That's what you would look for in terms of your software documentation. The alternative is long to wide. The variable that I want to reshape is outcome. You would list each one that you want here. The variable that tells me who is person ID, and the variable that is going to be created based on the end of the variable name is going to be occasion. So the way Stata works in particular is that it looks for stems. So like I named these on purpose because I knew it was going to do this, like outcome 1, outcome 2, outcome 3. It's going to take the number off the end of it and save it as that column in your data set for occasion. So that means that to use this, you have to have outcomes that are neatly organized and labeled as such. I've been unsuccessful in fighting with Stata against that, and I usually just change the variable names if I have to, because sometimes it's just easier to work around a problem. So this little line of code right here does everything you need. That's it. And Stata documentation is generally pretty good. So I'm throwing labels on there like the good data analyst that I learned to be. And then last but not least, I am centering my variables so that 0 is meaningful. In the original data, I have group 1 and I have group 2. And in reshaping to long format, I have occasions 1 and 2. Well, if I put those variables in the model as is, my intercept would be for group 0, which doesn't exist, at a time before pretest, which doesn't exist. Likewise, the main effects of the variables that are part of interactions would be conditional on the 0 values that don't exist. So we're going to fix that. I'm going to subtract 1 from each. So I have a new variable. This one should be, why is that there? That one should be occasion. That's a typo. I will fix the files online and repost later. So occasion -1 is now a variable we're going to call time. where 0 is pre-test, 1 is post-test. And group I've renamed with treat because that's what 1 means. So 0 is control, 1 is treatment. And I throw the labels on there. All right, any questions on Stata code? All right, our folks, I didn't leave you out. So setting working directory, importing from Excel, making sure it's a data frame because sometimes they're imported in other formats and it doesn't play nicely with other formats. Then grammar. Do not correct my grammar on this word. R is very picky about the conventions here. So I'm going to use something I found in base R called reshape. I know there's a bunch of ways to do this in the tidyverse, and I'm deliberately staying away from those. So I am starting with a data set that I named example 3A wide. The end result of this is just example 3A. So that's the long format that we'll be working with today. The direction that I want it to go into is long, from wide. The names that I want to transpose, just outcome. ID variable is which person, time variable is which occasion, and then which ones are the varying ones, and then what are their times. So if a little bit more typing to do it this way, but I like it because it's fairly transparent what is happening here. So if you had more than one variable that you needed to transpose, you could just add these into the list, like separated with like the C function, for instance, for this part, the concat function. Centering predictors then. In R, unless you use a workaround, every time you make a new variable, you have to tell it what data set the variable goes to, because you can have many data sets and objects active at the same time. So I always just leave the name of the data sets to make sure that my code will run. So example 3A $, and then time is the new variable that's being created from the old variable -1, and likewise the new variable treat. And here are the labels that I would have put in, but R doesn't like labels. It yells at you sometimes in certain packages if you have them. And then I sorted because that is needed for correct printing of the R matrix later on. All right, any questions about that part? All right. Then, description. So I'm using tabulate in Stata to get the cell means, and so this is what made that slide. 15 with all the cell means and all the marginal means and stuff. You can do the same thing. In R, I'm using the describe by function from the psych package, and that does not list the marginal or overall means, but it lists the means by occasion. So you can see that we have occasion 1, group 1, occasion 1, group 2, and so forth. So it does look like, just straight based on the means, that the treatment group improved by about 8 points over time, whereas the control group only increased by 5 or 6. So just eyeballing it, looks like the hypothesis is in the data are in the direction that would support the hypothesis. So building up from scratch then, first model, simplest model, E only. This is what this would look like. In new software that we're going to be using this semester, mixed within Stata the entire time, and in R it will depend on what particular model I want. There's 3 or 4 different packages that you will see being used. So outcome is the name of my one column that holds the data for both occasions. There's no predictors that would follow it, so that's why I just have a comma with nothing. In Stata, this bar thing, that is your, hey, how do I group the rows together? What's the column that attaches them across occasions from the same person? And it's person ID. The space after it is where you would put any random effects that you want. We're not going to have any of those yet. But it goes there by default with an intercept. So the first thing that I have to do to fit this model is shut that off with no constant. And I'm using the 3-line thing to be backwards compatible with older versions of Stata. I don't believe you have to do that after, what, 17, 18? Remember the 3-line thing? 16? Yeah. Well, I'm still rocking 14 at home. I bought a perpetual license a long time ago, and I intend to use it in perpetuity. So very few things have changed relative to Stata 14, and I still have this convention in there. All right. REML is the name of our estimator. We haven't talked about that yet. It is the default, but I have it in here for transparency. It is functionally the same thing as ordinary least squares if you are fitting single level models that are general linear models. Now, this is the part that we care about today, residuals, meaning what kind of correlation pattern are we going to allow for outcomes from the same person? Independent, can you guess what that means? What kind of correlation? 0, independent. So this is another way of thinking about a standard linear regression model. You are saying that all of the E's are uncorrelated across all the people. Here we're saying it across the people and the occasions. As a jumping off point, the T in the blue there is saying, hey, what variable do you want me to use to keep track of which occasion is which? And it's called occasion in this case. For this model, it doesn't matter, but for other models that have distinct patterns, it will matter. No log shuts off part of the output that I don't want in terms of the iteration history, so that will show up in my programs. And degrees of freedom in Stata are not the default. It gives you z's and chi-squares by default unless you ask for it to use denominator degrees of freedom, and so I'm using residual for right now, which is your least squares version. So that's a very, very long way of saying I'd like the mean and variance of this outcome back, please, because that's what I'm going to get. It is. Ironically, this is one of the few days where both classes are learning the same thing. The regression class is going to see their very first regression model as this one. Not from this perspective, though, but empty models. So, underscore const, that's my fixed intercept. So on average, across all the occasions and all the people, my outcome is 53. Cool. I don't really care about the rest of this. 53 is not 0, is what that p-value was telling me. Didn't expect it to be. And then this is the job security part in terms of how software labels things because their labels are not right. Random effects parameters. I don't have any random effects in my model. I have one E residual. So the 40 here refers to the variance of the E residuals, which is all of the variability in this data set for that outcome. Haven't explained anything. In your homework, I will ask you for -2 log likelihood for each model. This is how you can get it out of Stata. Stata gives you log likelihood instead, which is the height of the data given the model parameters. -2 times that is what we use to do model comparisons. And so it's easier to think things in terms of -2. Inside Stata, I'm getting better at this. I'm learning how to do math on Stata inside things. I've been working on that this week. I know, it's very exciting when you can finally make it work. And our people are like, yeah, yay for you. Like I've been doing that since day one. I'm getting better at that too. It's slow going. But this is like the internally stored log likelihood value from whatever you ran last times -2. So it's going to grab that number, multiply it by -2 for you, and then spit it out in your output. So you can save a step if you include this after each of the things you want to run. Okay. Any questions from Stata folks?
Yeah, what do you call that thing? What's the technical term?
Stored object, maybe?
Well, yeah, you're probably right, but
It's at the end of the documentation, it's always the last page, is what are the internally stored things, and sometimes they're R's, and sometimes they're E's, and sometimes they're H's.
and more broadly, that's called
Post-estimation command? Okay, that's what you call it? See, I think of those as like the lincoms and the means and
Yeah,
like
those
the,
are all
yeah,
post-estimation.
okay, post-estimation, that's the magic keyword to look
you need
for.
a model, and then you
Yeah.
can call specific things.
Right, you need a model
I
first.
thought you knew that, sorry.
I did know post-estimation, I didn't put this in that category.
Yeah.
Okay, now I know. And knowing is half the battle. G.I. Joe. No. That was a commercial when I was like 8 for G.I. Joe. Knowing is half the battle. Ask the YouTube about it. You can find all old commercials on there. All right, R folks, I got to be honest with you. You've heard me complain about R in other classes. For this class, it is the worst because there is not a single R package that will do everything I want at the same time. There's just not. I keep looking, expecting like someone's going to make one. And I thought I found one that did more stuff the other day. No, it doesn't do likelihood ratio tests inside. I'm like, come on. So this is going to be varying. But right now we are working with something called GLS, which is within the NLME package. GLS stands for generalized least squares. It is a multivariate modeling set of options. It allows random effects, but we don't have any yet, and which is why I have to use this, because all of the other routines insist on having a random intercept and you cannot shut it off. So within this function, I am saving the results of it as empty underscore BP. That's the name of my model. I'm telling it what data set I'm using, what method of estimation I'm using. Model, instead of formula for this one, equals outcome squiggle 1. Meaning, what do I have in my model? What does the 1 stand for? Fixed intercept. Yep. I put that in there to remind myself. You don't technically need to write it, but I put it in there. Correlation equals null, means no correlation. A diagonal R matrix. So we're saying that the two occasions have nothing to do with each other. That's our most naive jumping off point. I want it to show -2 times the log likelihood. It does not do so by default, so I asked it to do so. So that's the first thing. And then summary asks it to print the output from the analysis. So -2 log likelihood, that's the number you want to put in the homework system. Then we get information criteria and log likelihood. We haven't talked about those yet. Those are coming. Coefficients, just one, the intercept. That's my overall sample mean of 53, same number as we got out of Stata. It gives me residual standard error, which is not residual variance, it's residual standard deviation. So this is how far wrong we are on average in terms of our worst naive prediction. Total variance, though, is what I would like to report, the variance of the e's, and that's the number 40. And then I also threw a confidence interval in here just in case you care about those. I asked both Stata and R to print the implied R matrix by the model, and they're like, no, it's diagonal, figure it out. SAS is like, sure, you can do that. So this is another way of saying what our model is predicting for the variance and covariance across outcomes. Pre-test has a variance of 40, post-test has a variance of 40, and they have nothing to do with each other. That's what this model says. Unlikely to be true, but this is a point of comparison. So let's make it a better naive starting point, adding our new friend U0. So I call this a within-person model. You can think of it as U plus E in terms of the variance structure. This is a heading towards a within-group ANOVA, just without predictors. You can think of it that way too. So within the mixed package, I am still not using a random intercept yet. I am doing it in the residuals right now. So exchangeable is what Stata calls a R matrix that looks like, go back, this. This is exchangeable. Equal variance on the diagonal, equal covariance on the off diagonals. That's the pattern that we're asking for. So we still have a fixed intercept of 53. Standard error is higher now because this is a person level thing. It's the idea that each person has this random intercept, not here, but here. There's two different ways to put it in the model, and this is one of them. Then we get down to residual exchangeable, var E cov E. They're lying to you. I know. This is not var E. It's 40. It's total variance. It is the total variability implied from U plus E. The variability due to the U part is what they're calling cov E, and that is 12. So the 40 is very close to what it was before in terms of all of the variability being due to E. What we've done is split that up. So 12 of it is because of the variability of the U zeros. 12 of it is because some people are higher on average, and that means about 28 of it is due to the E's. So the first question would be then, is 12 a lot? Well, here's a significance test for it. We'll talk about that later on. It's a likelihood ratio test, and if you're like, is that the same thing that I did in all your other classes? Yes, it is. It's the difference in -2 log likelihood between the two models. Stata does it for you in this case. How about an effect size? So here, under SStat, W correlation, comma, covariance, that's my model implied R matrix. So now they show it to you in the form that is a little bit more useful. So 40 is what's on the diagonal, but now there's this 12 on the off diagonal. In correlation form, SStat W correlation without the option, that translates to a correlation of 0.303. That's our intraclass correlation. So I can think about it two different ways. One is as a proportion to total variance. So of all the reasons why some outcomes are different over time, it's 30% because of people. Some people are higher on average, that's 30%. The 70% that's left then has to be because one occasion is different than the other. So 30% is between, 30% is level 2, 30% is because of person mean differences, 30% is because of the random intercept. The other way to think about it is just as a correlation over time, and that's what's given this way. Occasion 1 is correlated with occasion 2 at 0.3. So the significance test of this intraclass correlation is done by saying, hey, what would the model look like if this wasn't here? And then comparing the two. So we'll talk more about that later on, but I just wanted to get the idea that we are allowing residuals to be correlated this way. All right. In R, I'm laughing. The difference right here. Correlation equals core comp sim form equals squiggle 1 bar person. Ask me how I figured that out. The Google. There's no way I would have figured that out myself. Like, give me a compound symmetry correlation in R. And it's like, oh, okay, well, you're going to need to type 17 things. But that's what it is. So another term for this is compound symmetry, this pattern, where equal variance equal covariance over time. Same everything else except for that part right here. That's the new part. Why don't I just make it new? Can I do the, yeah, where's my little thingy? There. There. Draw attention to it. I did that on the handout I'm building right now. Just do it more. So it tells you in the output, correlation structure, compound symmetry, parameter estimate rho, that's my 0.3. So it just gives it to you straight out. That's my intraclass correlation from this model. There's my fixed intercept as usual. And then if I want to see it in matrix form, I can do that. Get var cov is a function that returns the variance covariance matrix. So there's my 40 on the diagonal, my 12 on the off diagonal. And then the correlation version under core matrix, had to dig in to find it a bit. So within the model object, there was something called model struct, and within that, I found core struct. And then it asked for to pull the matrix out of that. So this is very tricky, at least for me in R, like to figure out how to get numbers out of it. I'm not good at it. I always end up needing someone's help. But I did figure it out eventually. So what's tricky about this in terms of teaching it is that like there's nothing else in your output that would tell you how the model is phrased. It just gives you this correlation and then you'd have to dig in to figure out what the variances are. So it makes it more confusing than it otherwise needs to be. All right, so there we go. let's add some predictors and see what happens to those. So I'm going to add in everything I could possibly add in. I have two binary predictors, time and treatment. Time is phrased so that 0 is pretest and 1 is posttest. Treatment is phrased so that 0 is control and 1 is treatment. And I want their interaction to be in here too. So I'm going to compare and contrast two models, one that just has E and one that has U and E. So you can see what changes and what doesn't. So the model itself is only going to tell me part of what I want to know. The rest of it I can get through linear combinations as shown below. And this is something that I do in regression that you may not have seen before, so I wanted to introduce it in a more limited context, because this gets scarier as your models gets more complex, as you might imagine. So beta 0, that's going to give me a conditional mean for the reference group, right? When all my predictors are 0, who is going to be, which occasion and which person is that going to be my predicted outcome for? And Zoomers, you can play along. I'm watching the chat. Not meant to be a trick, I promise. What's my reference cell or person?
Pre-tested and control group?
Yep, pretest in the control group. So that is why, if you look at the equation here, where everything is literally zeroed out. So I get the pretest mean for the control group. Well, what if I want it for the other combinations? Certainly. I can get that through linear combinations. So every mean starts with beta 0, and then the contribution of the main effect slopes, beta 1 and beta 2, and the interaction term, depend on which particular configuration I want. So if I want the control group at post-test, time turns on, still control group, so that stays 0, and then 0 times 0, or excuse me, 1 times 0 is 0. So I did it. I'm throwing in the things. I should do it properly, shouldn't I? I did the end result rather than the algorithm. 1 times 0 is 0, though, I'm pretty sure. The only time the interaction term turns on is when they're both 1. So there are various ways to get this, these predicted outcomes from you. I usually make them do it somewhat manually with LinCom statements or GLHT statements at first, and then you can use prediction and things like that to speed things along. This part, though, you may or may not have seen before. The idea of what is commonly referred to as simple slopes, which is a term I hate because this is complicated, not simple. These are complicated slopes. My model is only going to tell me 2 out of the 4 slopes that I might want to know about. Up here, beta 1 is the effect of time. Can I say that? Do I need to keep talking? Is beta 1 the effect of time the end? No. Conditional on what? Given the interaction term with treatment. Control group. That's the control group effect of time. So that is the way that I would get the time slope for either group. I start with what it is, beta 1, and then I go and find all the other terms in the equation that have that slope. There's only one in this case, beta 3. So what goes in the computation of these slopes is factoring out the variable the slope is for, putting it at the end, and then the multiplier is for the moderator of group here. So the time slope for the control group is just the time slope plus 0 for the fact that it's control. It's just beta 1. The time slope for the treatment group, on the other hand, starts with beta 1 and picks up the interaction term times 1 for treatment. So beta 1 plus beta 3 tells me what the time slope is for the treatment group. If I spin it the other way, if I think of group as the thing I care about and time is the moderator, then beta 2 is the group difference, ... What's the end of my sentence need to be? Beta 2 is the group difference when? Pretest, yeah. So beta 2 is only the group difference if I'm talking about pretest when the time moderator would zero out. It's beta 2 plus beta 3 to get to what the group slope would be at post-test. So we can get all the simple effects out that we want. The interaction term is either how the time slope differs by treatment or how the treatment slope differs by time, whichever way you want to go. So throwing all of that stuff in the model, in Stata I am using CDOT for all of these to make them be treated as continuous variables. Since they're all already dummy coded, that's fine. We're back to independent residuals in this example, since it's just E. If I wanted to get a hypothesis test for my model, here's how I would do that in Stata code. The test command says, what if the time slope were 0, the treatment slope were 0, and the interaction term were 0? Then what would happen? The small means use degrees of freedom for the denominator. That means turns it into an F. These lincom statements then do all of this. These linear combinations is what is happening right here. And I wrote all of the possibilities out so that it would be, you could see the pattern, but obviously you don't need to type ×1, that's implied. And you don't need to type anything ×0 because that would drop out, but I'm matching the format of it being up here. So I wrote all of them, including the interaction term, so that all of the coefficients I care about would be in the same place. Overkill, but useful for pedagogy. In R, my new model has picked up time, treatment, and time by treatment, where a colon is used to indicate a two-way interaction term. Alternatively, if you wanted to do less typing, you could just do time star treat, and that is all lower order main effects in a two-way interaction. Stata does that too with 2 hashtags, by the way. I tend not to do that when I'm teaching. And we're back to correlation equals null. All right, I just showed the R output because Stata output, if you've been through regression, you know how to read Stata output before. They look pretty similar in this case. So here's my results. So 49 is my new beta 0 intercept. That is my control group mean at pretest. The so-called simple main effective time of 5.8 is how much higher post-test is than pretest in the control group. So it looks like the control group grew significantly, hooray. Treatment is the group difference, how treatment differs from control specifically at pretest. And this p-value is not significant. Is that good news or bad news? If I have no group difference at pretest, that means random assignment worked. Yay! That's a good thing. Now the interaction term of 2. We don't talk about what happens to the outcome. We talk about what happens to the slopes, which then affect the outcome. So the way that I would interpret this is the change between pretest and post-test is 5.8 in the control group. It is stronger, more positive by 2 in the treatment group. I'll say that again. The change from pre to post is 5.8 in control. The change is greater by 2 in the treatment group. The difference of the difference. If I go the other way, the group difference is 1.68 favoring treatment at the beginning. That group difference grows by 2 at post-test. More positive. However, wah, wah, my interaction term is not significant. It's not even approaching significance. It's 0.33. Do I take my ball and go home? What if I could fix it without cheating? Wouldn't that be nice? I can. Let's think about logically what kind of variance each of these things should explain. Time should explain time variance or people variance. It's 141, so we're going with the softball version of these. Time as a fixed effect should explain time variance or people variance. Not meant to be a trick, I swear. Time variance. Group, is that a people thing or a time thing? The people thing should explain people variance. Treatment by time. That one's a little more ambiguous. It's actually a time thing because it's how people change differently. But in this model, all of the variance is in one pile. The leftover variance, we had 40 before, after the predictors were down to 27. That doesn't care whether it's people things or time things. It's lumping in all the error for all of these terms regardless of what source of variance it could logically possibly explain. So these standard errors may not be correct because they include contributions of variability that are irrelevant. Time cannot possibly explain why some people are different than each other. So that variance, that U variance, should not be part of that story. So it turns out, after you fit the right model, our conclusions will change. And I'll just leave that there for dun dun dun. Stay tuned. We can come back on Thursday and hear the exciting conclusion as to whether Lisa's fake data behaved like they were supposed to. So this is chapter 3, if you'd like to read along. It is literally following the same example and most of the same words that came out of my face. All right, 143. Any questions before we call it a Tuesday? All right, then thanks for being here. I will see you Thursday. Let me know if you need anything, okay? All right, have great afternoons. Bye, Zoomers.